In this example, we are going to take a look at Dijkstra's algorithm. So this is the implementation of Dijkstra's algorithm as provided in the lectures. As usual, let's just go ahead and copy this and try to go line by line and see how we can make it more readable. So I'm just going to remove this example data from here and focus only on the function. Now the name of the function is perfectly fine. It takes an adjacency list A and a root from which to calculate the distance, the shortest distance to every other vertex in the adjacency matrix. Now here's the first thing that I would think is worth changing. We calculate a value of infinity. No, it's not really infinity in the number theoretical sense, but it's essentially simply a number that is greater than all of the weights that are present in the graph. So essentially it's a number, or rather a symbol, that when compared with any other number turns out to be greater. So we see what we're doing here is that we're iterating over the keys in the matrix and trying to find out what are the corresponding weights, and then adding 1 to that value, to the maximum of that value, so that we get a number that is higher than every possible weight. All of this is order of n because you have to iterate through the numbers and then you have to find the max of it. So this is something that can easily be gotten around by simply using the infinity symbol that is available in the math library that comes in Python. So we're just going to remove this, and at the top of the file we are going to say from math import inf. And of course, because we are now using inf instead of infinity as the variable name, just let's replace infinity with inf, and there it is. Now here too, the next thing that we do is we initialize two dictionaries, visited and distance. Now the order of visiting may not necessarily matter here, but nevertheless, let's just keep it a list. And distance though absolutely must be a dictionary. There is no other way around it, because for each particular vertex in the graph, we need to find out what was the shortest distance to it. Now, in order to set the default values within the distance dictionary, we are iterating over the keys, and once again, which is an order of n operation, and we are setting the distance to infinity. So a better way to do that is to simply create distance as a dictionary comprehension. We can say vertex colon infinity for vertex in. That's it. We actually don't need to iterate over the dot keys method of a dictionary when you're iterating through it. And that's because when you iterate over a dictionary, you by default iterate over its keys anyway. So adding that dot keys is a little redundant and not required. So now we can get rid of this also. And then we say that the distance to the root is 0 because that's what we are starting from. And then again, for each vertex in the graph, we run this loop. As I just mentioned, the a dot keys is not required because when you iterate over a dictionary, you're essentially iterating over its keys. The dot keys just gives us an extra explicit iterator, which we don't really need in this case. Now the first thing that we do within the loop is that we try to find out which vertex has the shortest distance or the shortest cost if it is not being visited. And there what we're doing is we're calling the min operator, and we're saying that find the distance, minimum distance of a particular vertex in the matrix if it is not visited. And we could simply call this something like min distance instead of simply next d. That's essentially the minimum of distance v for v in A if v not in visited. Because remember that visited is a list, not a dictionary. And then what we do is we try to pick a candidate key, a candidate vertex, which should become our next root, which should become the next vertex that we go to. So again here, what we can do is keep next v list as v for v in A. If instead of not visited v, we can say v not in visited, and the distance of v is the same as next d, which we are calling main distance, right? So that's essentially our next plist. We can actually, for better readability, call it candidates. And then we say that if candidates is an empty list, then we break because there are no more candidates left. This essentially is the terminating condition for the loop. And then what we can do is call it next root is the minimum of candidates, right? Now, this is a little tricky because why are we, one of the questions that we might want to think about is why are we using the min operator on the list of candidates? This is simply because in the examples that we have seen, the vertices are integer value. And we simply want to, by convention, pick the candidate vertex that has the minimum numerical value. And this is not always true for graphs. In graphs, your vertices can be absolutely any Python object. They don't necessarily have to be integers or strings or anything like that, right? So instead of using min, which itself is an order n operator, we can simply say is pick the 0th element in the candidates list as the next root, right? You're welcome to test this out later. This is essentially a place where we have sort of avoided a minimum operator which adds an order and operation. And then what we're going to do is that we are going to append this essential line is marking the next root as visited. So what we're going to replace this with is visited dot append of next root. And then we are going to iterate over the matrix again, and then we say that for vertex and cost in A of next root, if vertex not in visited, then the distance to that vertex is the minimum of distance to that vertex and the distance to the next root plus the cost. And that's it. That's how we have finished this. There seemed to be some syntax error again. We forgot a colon just like last time, and there it is. That's our Dijkstra's algorithm, slightly simpler. Do test this out with this particular example data that is given here, and see if the original Dijkstra's algorithm and this rewritten Dijkstra's algorithm presents the same results.